So in this exam, we begin with a series of questions, as we often do, where we're trying to predict the products for a series of given organic reactions. And as we've said previously, one of the most important things to getting these questions right is being able to look at the reagents and know what those reagents do. And in part A, we immediately start with an example like that. We have sodium hydroxide and water. Water we know here, of course, is the solvent, and sodium hydroxide is something we would regard as a base. So with a polar protic solvent, which is water, and a base in sodium hydroxide, our initial expectation would probably be that this reaction would be E1. But if you notice where our leaving group is next to an aromatic ring. And so there's no hydrogens here. And because there's no hydrogens, elimination can't occur. So the only other option here is nucleophilic substitution. Now, can that occur at this position? Because this is a primary leaving group. And normally for primary leaving groups, SN1 as well as E1 cannot occur. But in this case, the carbocation is next to an aromatic ring, it's stabilized by resonance, and so this carbocation is perfectly fine to form. And then after we add sodium hydroxide, we will get benzyl alcohol as the product. Part B, we have LAH. LAH is a strong reductant, and the functional group that we normally reduce is a carbonyl. Now here we have an aldehyde, so it really wouldn't matter if we had LAH or sodium borohydride. Both of them will very easily reduce an aldehyde to give us an alcohol. All right, part C, we have the addition of silver nitrate and ethanol. And you may recall in lab that this was part of our first experiment. In that experiment where we were comparing the rates of various SN1 and SN2 reactions with different alkyl halides. And so these were the conditions that strongly favored SN1. However, our leaving group here is on an sp2 carbon. And hopefully you recall that both SN1 and SN2 reactions do not work on sp or sp2 carbons, and so this reaction won't work at all. All right, part D, we have potassium T-butoxide and T-butanol. That's a strong base in a protic solvent. So we're looking again at E1 as the most likely possibility. Our leaving group here is secondary and it's next to an aromatic ring, so it will form a highly stable carbocation, and we will get the elimination that we would expect. Part E is another reduction, but this time we have sodium borohydride, which is the weaker of our two reductants that we've learned about. And esters, we've also learned, are the harder functional group to reduce. So aldehydes and ketones we can reduce with anything, any of our hydride reagents, but things like esters require stronger reducing agents. And in general, sodium borohydride is not strong enough to reduce an ester. Silver nitrate and ethanol we discussed before was very good conditions for an SN1 reaction. The carbocation that will form at this position is highly stabilized, both because it's tertiary and its resonance stabilized by an alkene. And then finally, the important thing to remember from lab is that silver nitrate is not the nucleophile here. The nucleophile here is the ethanol. The silver nitrate is there just to help it ionize. Finally, in part G, we have an SN2, and these are the exact SN2 conditions we used in our lab experiment. So with a secondary cation, we know SN2 can work. The iodine will replace the bromine. But the other important thing to remember is that SN2 attack always occurs from the opposite face, so we get an inversion of configuration to form this product.